Consider this control block diagram on the whiteboard. So you have the reference, the feedback, comparison between them, and the error, which is actually going to the input of the controller. And the controller is actually of two parts, the gain part and the structure part, GC, which is actually controlling the plant, GP. And there is a feedback portion which has an equivalent transfer function, H. So this is the generic block diagram, control block diagram of a single input, single output system, and then we would like to do the root locus design. So we have done that already using Python. We would like to implement the same using Octave. So the method is as we have done before. We define the plant GP, we define H, these are given to us. And then you start by defining the structure of GC, structure of the controller, whether you want to have just plain gain or you want to have an integral type of control or a PI control or a PID type of a control. So define the structure and then we go about selecting the gain using the root locus method. So let us try that. So I will define some arbitrary GP and H for now. H we will take it as one by one. GP we will start with what we have been using with other examples. Define a structure GC and go through the process of obtaining K for a given plant using the root locus method. And once we have learned how to do the root locus method using Octave, we will then try to use a more practical problem, a system like the DC motor, and then see how we can control it. Let us now try to understand root locus design using Octave by writing a script file. I have on the left hand side here octave underscore rlocus.m, which we had used earlier. So I will use the same. I will start modifying that. On the right hand side, we have the Octave IDE itself. So let me clean up. Let me remove these things. Let me start only with the transfer function. So before that, some comments are in order. So let me write the comment. So this script file demonstrates the use of root locus method for designing digital controllers. So this is our starting comment. Then the required packages, we need to load control, we need to load the package signal, and then LU control. So then after that, let us clear all variables and clear the screen. CLC will clear the screen. And then now you define the transfer function of plant GP. Now the numerator polynomial NUM and denominator polynomial, these are in the continuous domain. This is the sampling time, 0.2 seconds. And I am using my C2D, continuous to discrete conversion, and obtaining the discrete transfer function. Now this I am going to rename. This is numerator GPD, numerator polynomial of GP discrete, denominator polynomial of GP discrete. So NGPD and DGPD will define your GP system. Next, let us define the transfer function of feedback part, H. So let me call that as NH. Right now I'm going to keep it as 1 by 1 DH, also 1. So it is just a unit gain block, and so this is what we have. So let us run this. Okay, so let us run this, and let me remove this delimiter semicolon, so we will be able to see what is the numerator and the denominator polynomial of GP in the discrete domain. So let me save that. So I am already in the directory here, and let me run that. Octave R locus. So you get NGPD and DGPD. So if you want to see the transfer function, so let us say sys GPD is equal to transfer function NGPD DGPD TS, and you see the transfer function. So this is the transfer function of that particular of NGPD and DGPD in the form of numerator and the denominator polynomials in Z. So next, we need to decide on the structure of the controller GC. Then after that, we need to decide the value of gain K. So these two steps, if we complete, then we get the controller KGC. So deciding on the structure of the controller GC, now this is a while loop. So while something, and you will have end while. So in the beginning, let us have a flag equals while. So when the flag is yes, it will be the pointer will be within the while loop. So let's say I do string compare case insensitive flag and while. So what it does is it string compares this variable flag and the string character while, and without case sensitiveness because of I, then you will see that it will be 1 whenever flag is while, and it will be within the while loop. So in the while loop, so we do the root locus of open loop system GPH. So let us find that first. I'll call it N GPH. I know the polynomial, the numerator polynomial for GP is known, polynomial for H is known. So we'll combine these two to get GPH. So it is nothing but polynomial multiplication, and which is nothing but convolution. Convolve NGPD, which is this, with this. So I will have polynomial multiplication, and this will give me the numerator polynomial NGPH of GP and H combined together. Likewise, TGPH is convolution or polynomial multiplication of DGPD and DH. So this will give you the numerator and the denominator polynomial of GPH. Next, transfer function of the controller, GC. Now this has to be inputted every iteration. So MGC, the numerator polynomial for the controller structure, input, enter numerator of GC polynomial vector. So in vector form. And you have that. So this will be displayed, and it will ask the question, enter numerator of the GC polynomial vector. So you can enter the numerator polynomial and likewise the denominator polynomial. So what I will do, I will copy and paste and modify, and this is denominator of GC polynomial vector like this. So now you have entered the numerator and the denominator, you have them both. So you need to get the entire loop, GC, GP, H. So that forms the entire loop. So numerator of GC, GP, H is convolution, polynomial multiplication of NGPH into NGC. Likewise, DGC, GPH, convolution or polynomial multiplication of DGPH and DGC. So this will give you the loop transfer function of GC, GP, H. K alone is considered as 1. Now you are ready to plot the root locus of the loop transfer function. So let us have the background grid, my Z grid. This is taken from the LU control, and then after that my R locus. So this is just only plotting the root locus. You are not going to extract any gain or closed loop pole information, just to give you an idea how it looks. The root locus, N, GC, GP, H, D, GC, GP, H. So this is the numerator, the denominator polynomial of the loop transfer function. So this will plot the root locus, and then after that the question flag. Do you want to continue or do you want to exit the decision making on the structure of the controller? So it is again an input. So let us say modify GC structure, controller structure. So question. So is it an yes or a no? And it is a string. So you can indicate that it is a string. So it's very powerful, the input statement. So based on what you enter, if you enter y, and it still continues in the while loop, and then it will allow you to edit the numerator and the denominator polynomial of the controller GC till you are satisfied with the structure, and then you can exit the while loop. Let us validate the script that we have written till now. Previously, we validated till this point, loading the various packages, defining the transfer function GP and H. Then we wrote this part of the code where we wanted to decide the structure of the controller. which is in a while loop. So let us do that and check if the code is working properly or are there any bugs that we need to debug. So let me type Octave or locus. Okay. So the first part is that it has cleared the screen and then cleared all the variables. You see that there is no variable in the workspace. It's now fresh. Enter the numerator of the GC polynomial vector. So which means that right now it is here. The pointer is here. And we need to enter the numerator polynomial of the controller structure. So let me put it as 1 by 1 for now. So 1 by 1. And next, enter the denominator polynomial. So that also is 1. On executing, the root locus is plotted. And as expected, we know this familiar root locus for this particular transfer function. On the background, you see that you have the z plane coming in. Now here the program is waiting. It is still in the while loop and it is querying. Let me move this up. It is here. It is querying modify GC structure, yes or no. So let us say that I would like to modify further, and again I will enter the numerator and the denominator polynomial of the controller. So now let me change the structure. So let me put a 0 here at z is equal to 1 and a pole at z is equal to 0. So you will see that the root locus will be attracted towards this because you have to place the 0 here. So let's say 0 at z is equal to 1, which is z minus 1, that is a polynomial. And then for the denominator, z is equal to 0. So we have the denominator polynomial. So let me execute that. So you see the modification that happens to the root locus, and you see that it is pulled into the unit circle. And here the program is waiting whether you want to modify the controller structure further or not. So you can keep on iterating it till you are satisfied and then you can come out. So let me give n, no, I don't want to continue further, and I come out. So we know that the script that we have written till this point, let me close this, is working. So we need to do the next part, which is decide on the value of the gain k, which will complete our controller, the entire controller design aspect. So right now here you have decided on the structure GC, and if you also have the gain k, KGC will form the controller. So let us write the program script for that part of the program. So now that we are able to get the structure, we can now write the script for obtaining the gain k. So I have moved up the file a bit so that it is visible. So here again we will have a while loop. So I will use the flag variable. I will make flag variable as y, and while string compare case insensitive flag and y, and we will have end while to complete the loop. Okay. So within inside we will, let's say I will display. I'll use the display function. So let me display on the screen. Select closed loop pole location. So this is the job that we want to do, and then let it come onto the screen. So that we can pick from the root locus that is displayed. So we close the root locus and then again rewrite the root locus. So for that, my Z grid, put in the Z plane as a background, and this time we will want the K value and the closed loop pole locations that we click. And now I will use rloc find. So here I'm going to use rloc find, which we discussed earlier. And what is the transfer function that you want to pass? The numerator and the denominator of the loop transfer function. So n gc gp h and d gc gp h. So this is what you will be passing, the entire loop transfer function. GC, the structure of the controller, GP, the plant transfer function, and H, the feedback portion transfer function. K is the only aspect which is not there, and that is what we would like to find out from the root locus. So all this is there, GC, GP, H, which we have already calculated here, and then passing it on. So my rloc find will also give you a cursor, crosshair cursor, where you can go and click, and K and P are picked. P is just for display to know where the closed loop pole locations are. K you will use further to do a validation. So we want n close. N close is numerator polynomial of the closed loop transfer function, g by 1 plus g, h. D close. So closed loop polynomial, the closed loop numerator and the denominator polynomials of g by 1 plus gh. So I will use the feedback command to obtain the closed loop transfer function. Convolution, I'm going to multiply the polynomial ngc, this is the gc, and ngpd into k, and convolution dgc dgpt. So this is the numerator and the denominator polynomials of the feed forward path, GC, GP. K is also in the feed forward path, K, GC, GP. So K is going to multiply only in the numerator polynomial of NGC and NGPD. And then you have the feedback path transfer function NH, DH. So you can find out a bit more about the feedback function by putting help feedback in the Octave environment. Then after that, now that you have the closed loop transfer function, you can check with a step response check. So do a step response for enclose, declose of the closed loop transfer function. It should settle at whatever you have designed for. If it is a unit step, and the error is 0, it will settle ultimately at 1, and then you can observe both the transient response part and the steady state response part. So this will conclude this while, and then we can ask the question: do you want to continue iterating on the value of k, or you want to quit and close because you are satisfied? So select different gain K. Yes or no? And this is a string. So let us say that we need to enter a string. So this completes this while loop. And after the while, what is it that you want? I want it to display K. I want it to display the controller system transfer function TF, NGC, DGC in the discrete domain using the Z domain numerator and denominator polynomial. So this would complete the Octave script. Let me save that first. Let us now validate this Octave script file and check for this last portion that we added on deciding the value of the gain K from the root locus. So let us do that. So I'll go to the right side in the Octave IDE and type in this Octave file name, Octave R locus. So let us enter the numerator polynomial. I will for now write 1 and the denominator polynomial also 1. It's a 1 by 1 simple controller structure. Let me now come out of this while loop. So I will give no, then come out. So immediately the root locus is again reprinted, asking us here select closed loop pole location on this. So for me to choose a pole location, I will have to I will click somewhere here within the unit circle as close to the pole location and here, so that it remains within the unit circle. So let us click that. So you see that where I have clicked is K is equal to 1.6643 and the closed loop pole locations are almost 0.9 plus or minus 0.35. And you see this highly oscillatory nature because this is close to the unit circle, very underdamped, and settles down somewhere in between 0.4 and 0.5, close to 0.5. So it is not actually, it is just a 1 by 1 controller, it's not a PI controller where you get zero steady state error. This is just a pure gain controller where the controller is just K into GC. K in this case is, so let's say I come out of this. So you have K 1.66 and the controller is 1. So it is just a plain K, KGC is nothing but just a gain of 1.66. So it is going to definitely have an error, and that is why it is not going to 1. So this is the step response that you get. So this is how you would go about doing a root locus gain selection, and apparently what we have just seen that the gain selection is working. Now let us try with a real example, a real practical example like a DC motor, and see if we can design a PI or a PID controller for the same. In order to include the model of a plant, a generic complex model of the plant, I need to look at this portion. See, we have used a very simple transfer function here and then generated NGPD and DGPD. But this can be a complex transfer function, and this can probably be a function or another script file. So what I will do is, let me for the moment comment out these lines. So these lines are commented out, and instead I will say, let's say we want to model a DC motor. So I'll say DC motor. So I'll call a DC motor script. We will do that. The script we have not yet written. So let's say the DC motor script, the function of this script. So I'm calling a script within a script. You can also call a function. But Octave, in Octave, calling a script within a script is a powerful way of preserving the globalness of the variables. So this DC motor script we shall write just now. And to do that, okay, let me first save this, and I will open another new file, and I will save this as DC motor dot.m file. Okay, so we will save that, and it is a blank file. So now let us start writing the script here. So let me say this is a script file to provide the plant model. In this case, the model of a DC motor. So for this, so let me now, let's say, display. So I will display a string which says the values of the plant DC motor parameters. So this will get displayed. So let's say RA 2 ohms, LA 0.5 units of henries. So then KT constant, torque constant for the motor 0.1. I'm using the same values that I had used for Python. So Newton meter per amp. Then you have the B, the friction coefficient 0.2. This is what I had used. And J, the inertia part 0.02 kg meter square per second square. And then the TS, the sample time. So let me include the sample time also here in the specification. 0 seconds. So the small signal model of the DC motor we have already seen. DC motor, we have discussed this in previous lectures. So I'm just going to write that. So continuous model AC. So this is RA by LA minus KT by LA. The next row, KT by J minus B by J. So this is the A matrix, AC matrix, and you have the BC, which is 1 by LA, 0, next row, 0, minus 1 by J. So this is the B matrix. I will close that. Then C matrix, all continuous domain values which I am trying to indicate. So we are taking the output, which is the state vectors, in this case here IA and omega. We are taking the output as omega, BC, and that is keeping 0. No direct feed forward component. So this is the state space model of the plant, which is the DC motor. I can also give here U label label of inputs. What are the inputs? V voltage and TL. These are the input labels. So when you print the matrices, it will do pretty printing. Y labels. So Y labels is nothing but output omega, and X labels so you have IA as one of the state vector, omega as another state vector. So these are the labels. Okay, so now the continuous time transfer function of the DC motor. So what is this? So I will say TF. So I will say TF DC. Now it's a TF DC. Again, the zero pole form, zero pole gain form can do that. And then I'll use the TF command function. And then inside I need to use the system, the state space, which is AC, BC, C, C, D, C. So that will give me a system, the state space system, and then I will use the TF to convert it into the transfer function form, and then finally I will display it as pole zero form, gain pole zero form. So that is ZPK. An interesting function too. I will not give a semicolon. We can see what that is. If I do not give a semicolon, it will get displayed on the screen. So next, another conversion. Let us do conversion from continuous to discrete domain. So the discrete domain matrices A, B, C, D. These are the discrete domain matrices which I would like to have my C to D. Recall that I'm using my C to D again here. Last time when we used my C to D for transfer function, I gave numerator polynomial, denominator polynomial. I can give the state matrices also. AC, DC, CC and DC along with sample time. So I pass all these parameters and I obtain the discrete domain state matrices. So just like we argued in the Python while doing the Python modeling of the DC motor, TL input is considered as disturbance. So the V input or the armature voltage input is considered as input to the system. So I'll just indicate that here so that we don't forget. So we take the B matrix and we take the columns, all rows of column 1 corresponding to the V input, and the D also we will consider only with respect to one of the D, all rows of the first column. Same thing here also, all rows of the first column. So you are considering the armature voltage only as the input. So next we need to get the NGPD and DGPD. So this you are getting from state space to transfer function. from A, B, C, D. Modified B and modified D is used. And this will give the numerator and the denominator polynomial of the discrete transfer function of the DC motor. So this is what will be used further for doing the root locus design. So the discretized version of the plant, of the DC motor plant, is here, and this is the numerator polynomial and this is the denominator polynomial. So some amount of displaying can also be done. So let's say display. So I will say display the transfer function in Z domain. I can use that. Okay. So let's say T, the transfer function of the DC motor in the Z domain is equal to ZPK. I can use that. TF NGPD DGPD TS. So that will give you a display in zero pole form. So I can also print this pretty print in the state equations. I will print sys A, B, C, D, U labels, Y labels, X labels. So this is a nice way of seeing the state equations of any system. So that is why we have used these three labels here. So you will see when you see the output. So let me save that. So this is the DC motor script, which will give you the model of the system. We can run this and then see how this looks like. Let us now check out this script file. Let us validate this model. Let us run it in the Octave environment. So on the right side, we have the Octave window, Octave environment window here open, and I will type in the DC motor file name. So when I execute that, so you see here the values of the DC motor parameters displays here. Values of DC motor parameters, RA, LA, all those things, all those values are displayed, so you get an idea what it is, and then followed by the small signal model. So this is the small signal model. Followed by that is the continuous time transfer function of the DC motor. Now that continuous time transfer function, you have two, because you have two inputs. One is the armature voltage input and the other one is the torque input, which we are considering it as a disturbance input. That is TFDC here. So the state space is having dual input. Then followed by that, you have the transformation conversion into the discrete domain TFDCZ, and for that we are considering only one input, and that input is the armature voltage input, and we are not considering the TL input. So that is what we have done here. So this NGPD and DGPD which you are getting is single input, single output. So this is the transfer function of the DC motor plant with input as armature voltage, and the output is omega. And here you see this print sys, so which you are able to see the state space formulation or the state space model of the DC motor plant. So you have the A matrix. These labels are pretty useful here. You see the state vector, and you have the input vector, only V here, and the state vector. Same way here for C and D also. So it gives you a nice visual feel for the model of the system. So that is why we used these labels and this parenthesis. So this is the DC motor model, and you can have more complex models and then you can put them in a file, script file like this. And what we have done with that model, so we are going to call that as a script within this root locus controller design script. So we have put that in there. So that is how you would use plant models, probably designed by others, probably designed which need a separate file because they may be pretty complex. You can have a separate file for that and then call them here. So now we will run the root locus design script, Octave or locus, and see how we can design a compensator or a controller, discrete controller for this. I shall now go into the DC motor script file, and I shall put a semicolon here so that I don't want to see the transfer function, continuous domain transfer function now. And I can also comment out the parenthesis so that for the moment it doesn't display on the screen and clutter up the screen. I would like to see the transfer function here. Probably I would also like to see the parameters here. So let us save that, then go to the Octave or locus, that is the root locus design script file. We have the DC motor here, and in the Octave screen, I will say clear screen, and that is clear. So let us run this Octave or locus and do a controller compensator design using the root locus method. I will call now Octave or locus. So the DC motor plant script file has executed, and these are the plant parameters, and you have the transfer function here. And after doing the transfer function, so it has come here and requesting us to enter the numerator of the controller polynomial. So if I put 1 and 1 for both the numerator and the denominator, so you will see the root locus of this plant. So it has two poles, and it has 1, 0 here. So 0 is, other 0 is at infinity. Now, I don't want to do just a plain gain controller. So let us do a PID controller, one integrator and one integrator and also a lead network. So for this, I will want to modify the structure. Let me go at it again. So the numerator will have two zeros, the PID, and you will have two poles. So let me put in the two zeros. So I will give it as convolution, and there are two zeros. So first zero. So first zero is Z minus 0.95. So I am trying to break this pattern here. I am going to break this pattern here. 1 0, 1 0 I am going to place close to this pole. Another 0 I am going to place close to this pole, so that I break this and try to bring the root locus inside. But if I break this by placing zeros here, I need to place poles. So one pole I will place here as an integrator pole, and another pole I will place here at Z is equal to 0. So that is the plan. So at around 0.95 and 0.9, I will place the zeros. So 1, minus 0, 0.9510, another 0 will be 1, minus 0.9. So it is at that point, so that I will split that, split the root locus at that point, so that the poles terminate at the nearby 0. So then the denominator. So the denominator convolution, I need two poles here also. So the two poles are, the first one I am going to place at z is equal to 1 or z minus 1, and z is equal to 0, like this. So these are the two poles of the denominator polynomial of the control. So this is a control structure. This is a PID control structure. So let me execute that. So you will see that, here that this has, maybe you could zoom that, you will see here the zeros that I have placed. There is 1 0 that I have placed here. I have placed a pole z is equal to 1, so that comes in and terminates at the 0, 0.950, which I placed here, the 0.950. Then there is one pole 0.92 of the plant, and it will terminate at 0.9. There is a 0.90 which I placed here. So that is broken up now, and we can use this structure. So let me go forward. So let me now come out of this while loop of iterating the control structure. Now let us go and choose the gain. So this is the root loci. So let me choose a gain somewhere inside, close at this point here. So let me select that. So the gain is 78.686, and these are the closed loop pole locations 4. You see there are already 2 poles by the plant, 2 poles by the controller, and therefore overall there will be 4 poles. These are the 4 closed loop poles. So this is the, you see that it is going to the steady state at 1, and that's a very good response. So you can choose different gains also. So let us say we try another example here. Let me say I want to choose a different gain, which means that yes. So you can probably choose something here and choose that. So gain is 103, and you see that slightly faster response. So like that you can do, and I will come out of this loop, and this is the controller. So you have gain of 103, approximately 100, and the controller is of this form: denominator z square minus z, or z minus 1 into z, and the numerator having these 2 zeros. So this is the controller. So this is how you go about designing PID controller or a P controller or even a simple K control, proportional control for any given plant, and how you model the plant and call them within the root locus script.